Determining the shelf life of dairy products. My name is Steve Flint from the School of Food and Advanced Technology at Massey University in New Zealand, and I look forward to sharing with you some of my experiences with judging shelf life of dairy products. In reality, this is probably the main question I have from industry in terms of industry consulting, in terms of how to determine shelf life, how to go about doing accelerated shelf life tests and so on. So I really think that you'll find this quite interesting. There's certainly a lot of things we can cover in this, but I'm going to try and limit it to something manageable today. So the outline of the talk is firstly, how do we define the shelf life of foods? Secondly, talking about shelf life testing and giving you some examples of how we do that. Talking about accelerated shelf life testing, and I'll give you a bit of a heads up in terms of a trick you can do once you've actually got some data around shelf life testing. And then predicting shelf life under different conditions. So different conditions of maybe temperature variability during transportation to a market and so on. So there's a few things I want to cover today, but I'm hoping that some of these, or if all of these things will interest you today. So what is shelf life? Well, shelf life is how long a product can maintain the qualities that you want out of that product. So it's the length of time the product can be stored under the conditions that product should be stored under, and retaining the quality in terms of safety, most definitely, but also sensory and functionality of the product. And in reality, in the dairy industry, generally our products are safe. We have pasteurization, we have good control over the hygiene of our manufacturing plants. So most of our shelf life issues are really related to sensory deterioration, functionality deterioration, and basically a deterioration in the quality of the product that customers expect. And of course, this will happen over time as any product is stored. Dairy products are perishable products, and they will all perish to a certain extent over time, depending on the type of product. So shelf life determination depends on a number of different factors. So the one that comes to mind, certainly for me, is microbial growth. And of course, milk and dairy products are very suitable for microbial growth. Microbes grow extremely well in them. And as a result of their growth, that will affect product quality. The second point is enzyme activity. And enzyme activity can occur from the milk itself, but the most important enzymatic activity actually comes from the microbial load that we find in product, because the enzymes produced by microorganisms are heat stable, they'll survive pasteurization, they end up in the final product, and as a result of that, we have deterioration over time due to fat and protein breakdown. So enzyme activity is something that will really judge the shelf life of a product, or limit the shelf life of a product. Moisture absorption is a problem, particularly with dried products, milk powder, dried casein and so on, dried whey powders. And we try and avoid that moisture absorption through packaging and so on. But that is a measure of deterioration in terms of shelf life. Chemical reactions like oxidation also reduce shelf life by affecting the sensory quality of the product. Physical and functional characteristics, often linked to enzymatic activity or some other deterioration in the product, but certainly producing a product that has characteristics that consumers do not expect from that product. And number 6 is probiotic viability. There's more and more dairy products these days that are incorporating probiotics, and maintaining the viable number of probiotics up to a limit that consumers expect is a challenge, because these are live bacteria that will die over time in the product that they have been added to. And that deterioration will vary depending on the type of probiotic, depending on the type of product and so on. So if we look at something simple as we see on the right-hand side of the screen, and we look at milk in general, so we look at unopened, all unopened milk, unopened whole milk, unopened reduced fat and skim milk, and unopened non-fat and lactose-free milk. So a variety of different types of milk. And we look at how long these traditionally last for. And you can see the time varies depending on the type of product. And there are a variety of different reasons for that. But these deterioration factors depend on a number of things. A lot of this time is based on historical experience, and that will also depend on, of course, the temperature at which we store the product. So these are just guidelines. They're guidelines that we accept as being standard for these types of products. Factors affecting shelf life, we've alluded to this already, but temperature is probably a big one. And you can see in the graph on the right-hand side of the screen, we're looking at the effect of different temperatures represented by the colored lines on the graph. And we've got a guide here in terms of the level of spoilage, which in this particular case is regarded as unacceptable. As the temperature increases, we see that the rate of, in this case, protease activity also increases. So the higher the temperature, the greater the deterioration. And that's no surprise to us. I think we all recognize that. Then we have water activity. So the water activity of a product will influence the shelf life of that product. The water activity will affect microbial growth. To a certain extent, it will also influence enzyme activity. Although surprisingly, enzymes can also act in very, very dry products, such as milk powder. That can deteriorate under normal store conditions through enzyme activity. Exposure to oxygen, which causes oxidation, the effect of packaging. So packaging's a pretty important guard, if you like, from the environment, from the extrinsic environment that can influence the quality of product, protecting against oxygen, protecting against moisture, and so on. And in some cases, protecting against light too. The actual intrinsic properties of the product. So if a product is more acidic, that will certainly influence the growth of bacteria. Bacteria tend to not grow so well in an acidic type product. So the intrinsic properties of the product will influence the growth of bacteria. That may include things like the structure of the product, the chemical nature of the product, and so on. The preservatives in a product, and in a product such as processed cheese, which we'll talk about later, there are a number of preservatives that we add to that product, and the combinations of those preservatives will influence the shelf life of the product. Light, I alluded to earlier, is a potential problem in fresh pasteurized products. And of course, pH, we've already touched on that as well. Okay, so is shelf life related to food safety? Well, as I said earlier, generally no, because we regard our foods as being fairly safe after incorporating pasteurization into all our manufacturing processes, and with the strict hygiene risk management plans we have in our manufacturing plants. So it's not normally a problem, but there are certain situations where it may be a problem. And those exceptions are listed on the screen. So spore formers will survive pasteurization, and Bacillus cereus growth in a product can be an issue. One product where this has been a particular issue in the past is in dairy desserts. So these are dairy-based products that often have starch in them to gel them up. And those products do support the growth of Bacillus cereus. They tend not to be a low pH product, they're more of a high pH product. This organism can grow, produces toxins, produces sickness. So some consideration is needed there in terms of the shelf life of dairy desserts and the risk of Bacillus cereus contamination and growth. The production of toxins from organisms like Staphylococcus aureus, that is also a food safety issue, and most of you will be familiar with the snow incident that occurred in Japan some time ago, where we had Staphylococcus aureus toxin causing an issue in the product. Handling abuse, so handling is a big problem. We know how to store dairy products safely, but there may be issues where product isn't stored correctly and contamination can occur, and hence there are food safety issues associated with that. And specific formulations with added risk factors. So we've talked about dairy desserts, but there are other various formulated dairy products that can have additional food safety concerns. And so in those situations, shelf life and food safety are something we need to consider. And I'll give you an example of a processed cheese scenario that we worked on some time ago relating to food safety and shelf life. Okay, so two things I want to mention here, and that is the general regulations relating to shelf life. And this links into the food safety thing I was talking about before. And these are two terms that are often very misunderstood by the general public. So the first one is use by, and that is the date referred to as a possible food safety limit. So when a product has a use by date on it, that means that product should be consumed by the date listed on the packet. Best before date is somewhat different, and that relates more to the quality of the product, excluding a food safety issue. So products can often be consumed after that use by date. They may not taste the same, so you may regard them as products that have deteriorated in terms of shelf life, but they're still safe to eat. So those two terms I think are particularly important, and they do relate to how we judge shelf life. Are we judging shelf life based on food safety? Therefore, we're trying to determine the use by date, or are we trying to relate shelf life to a general quality indicator, in which case we're looking to define a best before date. And of course, these dates are assuming that the product has not been opened, so the product remains packaged as it was when it left the manufacturing plant. Okay, who's responsible for calculation of shelf life? Well, the manufacturer is really responsible on a day-to-day basis for the shelf life of the product. And by consistent manufacturing processes, we generally know through the historical performance of our product what the shelf life of that product might be. The researchers who develop new products need to determine what the shelf life of that product is likely to be, and often through some extensive experimentation to determine that shelf life. And this is where I often get contacted by companies saying, well, we've got this new product, what's the shelf life likely to be? How can we do an accelerated shelf life test, and so on. The retailer and the supply chain have important roles to play in terms of the shelf life of a product. So while we as manufacturers and researchers may have a good guideline in terms of what we expect of that product, if that product is not stored correctly through the supply chain and managed well by the retailer, then there are potential problems in the shortening of shelf life. So whenever we determine a shelf life, it has that assumption that it will be looked after correctly by other people in the chain, such as the retailer and the supply chain. And of course, the consumer and the customer play a key role in the shelf life of the product too. If they don't store it correctly or they misuse the product, then there are issues there as well. I don't think I have any really good dairy examples for that, but I certainly have many other examples where consumers have abused product, and in some cases it has caused very serious issues in terms of their health. Okay, so who influences shelf life? The raw material providers. So in the dairy industry, we do rely a lot on farmers in terms of the quality of milk that comes off farm, how they store that milk. But one of the key issues that we've had, certainly in New Zealand, is the transportation of milk over long distances and how that milk deteriorates over time as we're transporting it to the manufacturing plant. And that can be a big issue, and that relates to one of the scenarios I'm going to talk about later today. In terms of the manufacturers, how we store the milk on site, how long we store it, whether we have temperature control on site before we actually manufacture the product, that will determine the shelf life of the product through the growth of microorganisms, through the production of enzymes and so on. Plant hygiene. Generally, our plants are in pretty good condition, so that should not be a problem. But if there were a problem with plant hygiene, that would also affect shelf life, simply through the contamination of product as it's being processed. And changes in process parameters. So if there's a change in terms of how a product's being processed, maybe it has to be processed in a slightly different way because of equipment breakdown or some other issue in the plant, that can also affect the shelf life of a product. But provided the manufacturing process is consistent, then we should be able to guarantee a consistent shelf life from a well-known product where we can clearly define what that product contains and we have a good historical perspective on that product. The customers, consumers, and supply chain will all have an influence on the shelf life through the storage conditions and the handling of the product. Okay, factors influencing shelf life. Every product has a standard or expected shelf life. So we know that with simple pasteurized milk, we can put a best before date on that product, and we can be pretty assured that that will survive in the marketplace to that particular date that we've nominated. And shelf life is, as I said earlier, often based on our historical experience with the product, but that is altered by the raw material variability and whether the product is being stored correctly, variations in the manufacturing process, and this can be something simple like delays or breakdowns, and variations in the formulation and they are based on intrinsic properties of the product, which may change from time to time. And I guess one of the issues that we do have with, say, small cheese manufacturers is you're making a variety of different small cheeses, and they all have different intrinsic properties. And all those different intrinsic properties will certainly influence the shelf life of those cheeses. And I guess the cheese manufacturers know through historical data how long these cheeses are likely to store under certain conditions. And of course, storage of cheese is important for cheese ripening anyway. Okay, so a shelf life study, if we want to determine the shelf life of a particular product, we need to determine what will limit the shelf life. And we've talked a little bit about the different categories, enzymes, chemical deterioration, microbiological growth, and so on. What tests do we need to do to determine shelf life? Sensory tests can be done, microbiological tests can be done, chemical tests, and physical tests. So all these tests will give us a guide in terms of what shelf life we can expect to get out of a particular product. But of course, all these tests do take time. Time to store the product and test over a period of weeks or months, and that can be quite costly for us. And there's really no way around doing that initially when you first are faced with a product and you want to determine its shelf life. You do have to do the hard yards in terms of looking at how long that product can be stored over a period of time. So when you do these studies, you need to plan them very carefully. You need to plan the time of the study, the frequency of sampling, the temperatures under which you want that product to be stored, the temperatures you're expecting through the supply chain and the market, and the number of replicates you have to do, how frequently you're going to test, and so on. So a carefully planned study is quite important for a new product where you want to determine shelf life. Then you have to run the study, which can take some considerable time. Determine the shelf life, establish the acceptable limits for that particular product, and monitor that shelf life to account for batch-to-batch variation. So it's no good just taking one example of the product. You need to consider the shelf life over time. And once you've actually got some basic data, then maybe you can test less frequently on subsequent batches of product to give yourself a guide in terms of how well that product is likely to store over time. Okay. One thing we do in certain circumstances, particularly if we're looking at the potential for a product to be safe, and particularly a product where we're allowed to add preservatives or some factors that are going to inhibit or prevent the growth of microorganisms, is challenge testing. So challenge testing is a bit different to normal standard shelf life studies where we're looking for general deterioration. It's where we actually add an organism to the product and see whether that organism will grow in that particular product. So it's often used for the food safety type shelf life studies. And it gives you an example of, what if this product is contaminated with this particular organism? Will it grow or will it not? And one of the best products we can use as an example for this is processed cheese, where we have a fairly well-known process for making the cheese, and we are able to add a number of different preservatives to that product to ensure the safety of that product. So what we do with challenge testing is we develop a scenario that you don't normally expect, or variations in formulation, to determine what we can get away with in terms of the proportions of different preservatives that we're adding to the product in order to make a safe product. And I've got an example which we'll talk about next on this. So we inoculate with the organisms of concern, and we monitor growth and look at the deterioration over time. And this is often used for new product development. And the product I want to talk about as an example of this is one that we worked on a few years ago with a PhD student. And that was a challenge testing of a high moisture, low salt processed cheese, which was a type of product that a company in New Zealand was interested in the possibility of manufacturing such a product. And so we were looking at the different parameters and how we could ensure that a high moisture, low salt processed cheese could be manufactured safely. So the types of conditions that we're concerned about are the pH, the moisture content, and the water activity, the basic parameters associated with that product. And the key organism of concern is Clostridium botulinum. It's our worst nightmare when it comes to a product like this. It is a very real risk with a product such as processed cheese. And this is something that we decided to use as our model for ensuring the shelf life of a high moisture, low salt processed cheese. So the first step was to select the best preservatives that have an inhibitory effect on Clostridium botulinum and are allowed to be used in processed cheese. And the second step was to develop a predictive model that allows us to predict the effect of those preservatives and the environmental conditions on the probability of microbial growth. So in this particular case, we were looking at salt, and potassium sorbate, niacin, and lysozyme as 4 key components that would affect the preservation of the cheese. And of course, they have other effects as well. Salt is a flavoring agent as well as a preservatives, and an important component of the cheese anyway. We were trying to reduce that salt level, which of course reduces the preservation effect of salt on the product. Potassium sorbate, well-known preservative use in cheese, but needs to be used at a low pH to be effective. Niacin, which is probably the most widely used bacteriocin that's used in the manufacture of cheese, effective at less than pH 7. And lysozyme, which is also a natural preservative, an enzyme found in many food products and used in cheese and other foods to control organisms like Clostridium botulinum. Okay, so in order to get some information around the shelf life of this cheese and ensure that this cheese will withstand storage over a period of time safely, we need to use a model. Now, there are 2 types of models that we can use for this. And models are extremely useful once you actually have the data. It really helps in subsequent developments of products. So there are 2 different types of models, kinetic models and probability models, and I'm going to talk about both of them today. But for the food safety one and the processed cheese, what we're really looking at is a probability model. So the probability model is deciding whether or not a microorganism will grow. And in the case of food safety, particularly with Clostridium botulinum, we are concerned as to whether any growth will occur or not. We don't want any growth to occur, so we're looking at a yes-no situation. The kinetic models are more suitable for where we're looking at the growth of an organism, which may affect the quality of that product through enzyme deterioration or some other effect that may influence sensory and functionality of the product. We'll talk about those later. So with a probability model, we're looking at comparing different conditions. So in the case of this particular graph that you see on the screen, we're looking at 2 zones, growth and no growth, and we're looking at what we call a contour plot, which is represented by these lines. And the graph is looking at a relationship between water activity and temperature. And as the temperature increases, as you might expect, from say 10, certainly through to about 30 degrees Celsius, you can see that the zone of growth starts to increase. There's a bigger area here where organisms can grow. And as the water activity decreases, you might expect the zone of no growth to increase, which is exactly what you see. So, you know, these graphs follow what we'd naturally expect with the relationship between, in this case, temperature and water activity. And we can plot these out and get some really good data for different combinations, in this case of water activity, based on sodium chloride in this particular case, and temperature. Now you'll notice there's 2 lines on this graph. So the zone in the middle between these 2 lines is actually a transition zone. So it's a zone where there is a probability of growth. And of course, in the case of a processed cheese where we want to prevent the growth of botulinum and a food safety issue, we definitely want to be in the no growth area. So being in this transition zone is not an option. So we need to work within this area where we are confident that we'll get no growth at all in terms of the growth of Clostridium botulinum in that product. Okay, so with the high moisture, low salt processed cheese that I mentioned earlier, this project was a PhD student project. It took her 3 years to actually generate these models that you're seeing today. They've all been published. And you know, you're welcome to use these the models that she generated as a result of her study. But the reason I'm mentioning this particular study and the reason I'm mentioning the 3 years is it can take a long time to generate enough data to generate a model that you can use in subsequent product development. Once you've got the model, it's relatively easy to adjust the proportions of, say, niacin or sorbate to get a situation where you're getting no growth. So in this particular case, these graphs, or these graphs you see on the screen here, are looking at the effect of sorbate and niacin, but we're also looking at different conditions of salt concentration and also pH. So what you see on the screen is some examples of the contour plots at pH 7. So looking at pH 7, and where I've got the pointer now, we're looking at the effect of 4% salt, and we're looking at the relationship between potassium sorbate concentration and niacin concentration. So as this potassium sorbate concentration increases, and as the niacin concentration increases, we get a bigger zone, and this particular zone on this graph is a no growth zone. So as those preservatives increase, we get no growth. So we can be confident that combinations represented by this area in terms of niacin and sorbate at a 4% salt concentration at a pH of 7, that we're going to get no growth, and we can safely produce a product that will have a shelf life that will ensure food safety under those conditions. And as with the earlier example, we have 2 lines on the graph. In fact, we've got 3 lines in this particular case, but these 2 lines that I'm pointing to now, they represent the extremes of no growth in this case to growth down here, and the zone in the middle is that transition zone where there is a probability of growth. So for designing this particular product, we don't want to be in that area at all, because that's an area that we're really quite concerned about. In a situation where we have 0% salt, that area of growth is much bigger because we don't have the effect of salt. Again, we have a transition zone, and we have a much smaller zone of no growth where we have the higher sorbate and niacin concentrations. So all these different preservatives or factors that can have a preservation activity need to be compared, and data needs to be gathered in order to determine what we can use in terms of formulating a high salt, high moisture, low salt processed cheese. So again, we have similar graphs looking at the effect of salt, looking at the effect of niacin and potassium sorbate, this time at pH 5.5. So as you would expect with the lower pH, we have a much bigger zone where we can operate in to ensure that we have a product that's going to be safe and there's going to be no Clostridium botulinum growth. And you can see the comparison between 0% salt and 4% salt. The added effect of the salt is apparent there as well. And as a result of doing many of these comparisons, we come up with a formula. And this is called the logistic type model. You don't need to remember that really, but the key thing here is that you end up with a term here which is the probability of growth, and it's based on a number of constants which are determined experimentally, and you can combine those with your salt concentration, your potassium sorbate concentration, salt and sorbate concentrations, or salt and niacin concentrations, all these things to determine the actual probability of growth, whether you're going to get growth or not. And if anybody's really interested in this, if you're interested in making processed cheese and combinations of different preservatives in a high moisture product, these have been published, and there's an example on the screen of one of the publications that came out of this work. So that's data that's readily available. The models are readily available, and they would certainly help you in designing processed cheese type products. Okay, so let's leave that alone and talk more about accelerated shelf life testing. So shelf life testing involves quite a lot of work, and one of the concerns we have is the time it takes to actually generate the data that you need. And ideally, we'd like to be able to get that data sooner through accelerated shelf life testing. So what that means is that ideally, we'd be able to increase the temperature of storage of the product, and thereby increase the deterioration of that product, and get some sort of idea as to how that product would behave under normal circumstances. But in order to do that, we have to have a lot of data in order to give us the confidence in terms of what would happen under different temperature regimes. So the problems that we have with accelerated shelf life testing, when people always ask me, can we do an accelerated shelf life test? We really face with a number of problems, and those are listed on the screen. Often there's no valid kinetic data or model available for us to be able to predict what's going to happen under a normal storage situation if we increase the temperature. Like, what's that relationship between increasing the temperature and the deterioration of the product, and how does that relate to our final product? We just don't know. So there's often very little data available. If we have data available, then we can make some sort of prediction. Often there are too many parameters involved. So in terms of shelf life testing, it may not be just temperature. There may be exposure to oxygen. There may be a number of other factors, even exposure to light. A number of other parameters may be involved in terms of the deterioration of the product. In the case of cheese, of course, cheese is a living product, and there's a lot of things going on biochemically and microbiologically in that cheese over time. And so to actually do an accelerated shelf life testing on a cheese can be quite difficult because there's so many parameters to take into account there. And then the application of valid methods for an accelerated shelf life test too, determining what temperatures we should be using or what conditions we should be using, how frequently should we be sampling, all quite difficult. One of the things we can do if we're concerned with microbiological growth is there are models available online through the United States Department of Agriculture pathogen monitoring or pathogen modeling program, which looks at the growth of a number of different organisms in a number of different conditions of temperature and salt and so on. It doesn't cover everything, it covers some things. And a lot of the data on these commercial models are related to laboratory growth, so growth in laboratory media, which isn't really ideal in terms of what we're trying to do in the dairy industry. We're really most interested in what grows in our dairy products, and that's quite different to lab media. But it can give you an idea. So you can look at altering the temperature and altering the salt concentration and seeing what that does to the growth of an organism of interest, such as Bacillus cereus, and get a guide in terms of what's likely to happen if you increase the temperature in terms of the storage of your product. So they can be helpful, but they're not telling the full story, unfortunately. One thing I want to do is show you a situation where you have got some data on a product and how this can be very useful in terms of predicting the actual shelf life of your product. So the actual tool we use for this is called the square root equation. It's all based on the maximum specific growth rate of a particular microorganism. So you need to know, what the biggest threat is to your product deterioration. So if you know that it's, say, the growth of Pseudomonads, then you know the growth of Pseudomonads in this particular product, then you can actually use the square root equation to predict what's going to happen under different conditions of storage, mainly temperature. So it really involves modeling bacterial growth in chilled foods. That's what we want to focus on today anyway, and using kinetic modeling to do this. And the square root equation is, I think, quite magic in terms of what it can do. So just bear with me as we go through this, because I think the outcome is actually quite interesting. It certainly was very interesting to me when I first learned about it. So what we're really trying to do is look at the relative rate of deterioration or relative rate of growth under different conditions. So if we know what the rate of growth is at, say, 7 degrees Celsius, we can determine how much faster the product will deteriorate at, say, 10 degrees Celsius. So let me just take you through this briefly. So the square root equation, as I said earlier, is based on the maximum specific growth rate of a particular organism. So it's how fast that organism grows during logarithmic growth. And we call that mu max. And the square root of mu max is related to a constant, which we call B here, and then two temperature factors. So the actual temperature you're interested in, and the minimum temperature of growth for a particular organism. Now, the equation that's of most interest to us is this here, where we're looking at the relative rate of growth. So we're looking at comparing the mu max, the maximum growth rate, under a particular condition with a reference mu max for a particular condition. So it's something we know something about. And so the square root of R, which is the relative rate, is a comparison between these two terms here. So we're looking at the actual temperature of interest minus the minimum temperature for growth, the reference temperature we know a lot about, minus the minimum temperature for growth. And again, we're using that constant B that's experimentally determined. And the key equation here is this one here. So we take away that square root and we end up with R, which is the relative growth rate. And we're looking at the comparison between these terms, as we mentioned earlier. So it's these terms squared, and that'll give us the figure that we're most interested in. So let's move on and look at an example. So here's an example where at 7 degrees Celsius, you want to calculate the rate of spoilage relative to the rate at 0 degrees Celsius. So assume we know what's going to happen if we store our product at 0 degrees Celsius, but we want to store it at 7 degrees. So how much faster will that product deteriorate in terms of growth of a particular organism, say Pseudomonads, for example? And if we know the minimum growth rate of that particular organism, that is a key piece of information that we need, and that's published information. You can just get that. So there are some spoilage organisms, like some bacillus species, that have very low minimum temperatures for growth. Even Listeria can grow at less than 0 degrees Celsius. I'm using an example here where the minimum growth temperature for a particular organism is minus 8.5 degrees Celsius. Okay, so that's published information. You can just grab that. So if we take the 7 degrees Celsius that we want to know something about, we want to store our product at 7 degrees Celsius to see if we can develop an accelerated storage trial around that. We put that minimum temperature for growth, which is minus 8.5, into the equation. We use the reference temperature that we know, which is 0 degrees Celsius. And again, we incorporate our minimum temperature of growth for that organism, and we calculate that out, and we end up with a figure 3.32. And what that simply means is that your product stored at 7 degrees Celsius will deteriorate 3.32 times faster at 7 degrees Celsius than 0 degrees Celsius. So that is really quite helpful if you want to design an accelerated shelf life trial. And this table, I think, really puts it all into perspective. So what we're looking at here is on the far left, we're looking at a variety of different temperatures, and we're looking at a number of different conditions. So we're looking at the reference temperature, which in this case is 0 for these next two columns, and we're looking at a minimum temperature of growth, which may be minus 10 or minus 8.5 in these two different columns here. So at 0 degrees Celsius, that's our reference temperature. So the relative spoilage rate is 1, okay? And as we increase the temperature, that relative spoilage rate will increase based on that formula I showed you before. So we get to 7 degrees Celsius, and under the conditions we talked about on the last slide, using that formula, the product will deteriorate 3.32 times faster at 7 degrees Celsius compared with the 0 degrees reference that we have. And in the final column, what we've done here is alter the reference. So here we're looking at a reference temperature of 4 degrees Celsius, and we're looking at what's going to happen when we increase the temperature from 4 degrees Celsius to 7 degrees Celsius. So here we're going to see a situation where the product will deteriorate 1.54 times faster at 7 degrees Celsius compared with 4 degrees Celsius. And of course, as you increase the temperature, the rate of deterioration gets faster and faster. Okay, so that's if you've got a standard temperature, but what happens if you have a situation such as through the supply chain where the temperature varies? And we can account for that as well. So we simply sum together different formulae for the different temperatures that we go through during that transport or that shift in temperature of the transport chain or through different storage conditions. So if I move to the next slide, we're looking at a table where we have various different times in terms of hours. And we have the time at which the product is stored at different temperatures. So we have, in this case, 15 degrees Celsius. We've got 2 hours of 15 degrees Celsius, 1 hour at 14.7 degrees Celsius, and so on, all the way down. So as time goes on, the product is getting cooler in this case, but it's at those different temperatures for different times. So over a 24-hour period, we have a variety of different temperature changes in this particular product, and we can work out through that formula we saw before the relative rate of deterioration based on the minimum temperature for growth and the time at the different temperatures of 15 degrees Celsius and so on. So this is for 1 hour, and then because we're there for 2 hours, the rate's going to be twice that amount. And so we can multiply that relative rate by the time in the far left-hand column, get the figures that we see in the far right-hand column, and we total all these up. And in this particular case, with this scenario that we've developed, we see that the over this 24-hour period, we have an equivalent time of 74.8 hours, which is about just over 3 days, 3.1 days. So if we know that our product, and let's say it's a dairy dessert here, has a shelf life of 6 to 10 days at 0 degrees Celsius, under these conditions that you see in this table over that 24-hour period, that's equivalent to 3.1 days at 0 degrees Celsius, okay? So that whole change in scenario in terms of temperature and time is equivalent to 3.1 days at 0 degrees Celsius. So we know that the product will survive in terms of a shelf life for 6 to 10 days at 0 degrees Celsius. So is this product okay? Well, of course it is. It really has an equivalent time in terms of shelf life deterioration of 3.1 days. So this product is fine. So this is just an example of what you can do when you have some data and you have different storage conditions that you can monitor. You can actually get some useful information out of this. Okay, I want to finish off by just talking about a project that we did which has attracted quite a lot of interest, and it relates to enzyme deterioration of UHT milk. Now, we had a presentation on this through this medium earlier this year, a more complete presentation. So I'm just going to go through this briefly now, but it is certainly relevant to what we're talking about today, which is shelf life and measuring of shelf life. So this was really looking at the effect of protease enzymes produced by psychotrophic bacteria, pseudomonads in raw milk, and looking at the influence of those bacteria and the enzymes they produce on the final product quality in terms of UHT milk. So on this chart that you see on the screen now, we're looking at the effect of enzymes, just graphically the effect of enzymes on casein micelles, causing the breakdown of casein and the deterioration of product. This is another PhD project done by one of my students, Dong Sheng, and as I say, it's attracted quite a lot of interest. So these graphs are relating to 2 organisms that he found in raw milk, both Pseudomonads organisms, and looking at the growth of that organism in milk, in UHT milk. So we're using sterile milk for this exercise. So looking at what happens to this organism, how it grows in milk, and this is at 7 degrees Celsius, so the temperature is similar to what the milk may be from farm to factory. There's a variety of different temperature regimes possible there, but 7 degrees is a reasonable guide. So over a period of days, these organisms clearly grow, and during their growth, the enzymes represented by the blue bars also increase. So the number of enzyme units we can measure in terms of protease enzymes starts to increase. So you can see there's a relationship, as we would expect, between the growth of the organism and the production of enzymes. And as I said earlier, and as most of you will know, these organisms are quite sensitive to heat. They're killed by pasteurization, but the enzymes they produce are certainly not. And those enzymes can continue to act in the final product. Similarly, with this other organism, this is another one we did a similar study on. So looking again at the growth in milk over time and enzyme production over time. And the main reason for looking at these is that there is some variation between the different organisms, but there's also a lot of similarity there as well. So they all produce enzyme as the organism grows in the milk. Okay, so the shelf life determination of UHT milk is determined by monitoring things like the pH change in the milk, sedimentation, which is pretty obvious, the gelation of the milk, and protein degradation, which we can measure in various different ways. If you want to find out more about these studies, they've been well published, and are quite easy to access. So you can read a bit more about these studies that Dong did. I'm just taking you through a quick summary now. So in terms of gelation, you can actually see the gelation of the product. Many of you will be familiar with this. You will have seen it before. Visibly, you see the milk splitting as a result of that enzyme activity and the breakdown of protein. It can be pretty obvious, but of course, there's also deterioration before you get to that extreme stage, which can be picked up in terms of sensory analysis. We can also do HPLC assays to actually look at the protein profiles in the product and the deterioration in protein over time. And of course, the most clear observation through these graphs is the deterioration in kappa casein, alpha casein, and beta casein, where you have a high number of these cells. Clearly, that's quite different to the situation where there were no bacteria in the milk. You can clearly see you've got more of the different caseins in the product than you have when you have a high number of these enzyme producing organisms present. And of course, it varies depending on the amount of organisms you've got. So at 6 log colony forming units per mil, there is some deterioration, but it's nowhere near as much as when you get to 7 logs. But the next table, I think, is what's attracted most interest, because as a result of the work that Dong did, what we can now do is give a guide in terms of the number of bacteria, Pseudomonas bacteria in particular, but psychotrophic bacteria in general. So give an idea of the number of those bacteria that we have in the raw milk and how that is likely to affect the shelf life of a UHT milk stored at, in one case, 20 degrees Celsius and another case, 30 degrees Celsius. So with a milk, a raw milk that's ready for processing and has about 10 to the 4 colony forming units per mil of these protease producing bacteria, in UHT milk stored at 20 degrees Celsius, we can expect a shelf life of 8 months before we see that deterioration in protein and before we see such things as sedimentation and other factors that indicate protein deterioration. And an increase in temperature means that the enzymes work faster, and so the shelf life of that product is less than 6 months if we have that level of bacteria in the raw milk. And as we increase the number of bacteria in the milk, we have a reduced shelf life, as you would expect, but we can now give some real good guidelines around that. So if you have a product, a raw milk that has 10 to the 5 colony forming units per mil, in a warmish climate, you can expect less than 5 months shelf life of that product before there are noticeable changes in that product. And then when you get to 10 to the 6, obviously that's less, and 10 to the 7 is extreme. And you saw the total breakdown of the different caseins in the earlier graphs. So this sort of information is really useful, and I have given that to companies who've been interested in this, and they found that extremely useful in terms of helping guide them in terms of the production of quality UHT product. Okay, so the shelf life of UHT milk, we've looked at the protease activity. We know a lot about that now, which is really good. We know how to relate that to the numbers of protease producing bacteria at the start of the manufacturing process. But the limitations of this work are that, one, we're really only looking at proteolytic activity, and these microorganisms also produce lipase, which will also deteriorate the product and also limit shelf life. And of course, there's various different bacterial strains which will vary in terms of the amount of enzymes they produce. The other thing that we haven't looked at is phospholipase activity, and that's also an important criteria in terms of quality of product. So certainly more work to be done, but I think once you've done this work, it's really useful in terms of helping guide the industry in terms of shelf life. Okay, so I want to finish off with this slide, which gives you a reference, which I think is quite good. So if you want to find out more about food and beverage stability and shelf life, this particular publication is actually very good. And I would certainly recommend it. It's not a new publication, but it's readily available in libraries and on the web. And this will certainly give you some more information that may be useful to you. So shelf life is, as we all know, an essential quality indicator for product. It's important that we determine shelf life. It's important from the customer's point of view that a product has a shelf life and they can have confidence that product is going to meet their expectations up to that shelf life date. The validity of shelf life determination requires a number of things. It requires a determination of the specific requirements for product quality. So what are we really looking for? Are we really focusing on sensory issues, functionality issues, safety issues, and so on? We need to have appropriate data for a particular product, and I've given you some information today on some particular products, but if you really have a concern with a particular product, do a bit of a search on the literature and see if there's any information out there that may be relevant to your product and may help you in terms of guiding your food safety, or not food, yeah, maybe food safety, but certainly food shelf life, and also helping in terms of designing an accelerated shelf life study if you wish to do that. Understanding the product variability. So we know that our products do vary depending on raw material quality and so on and so forth. So understanding product and process, understanding raw material, understanding the variability that can occur through the manufacturing process and in market, I think is important too. Understanding the storage history of the product, which I guess is linked to what I've just said. But what are you expecting in terms of that product? And for us in Australia and New Zealand, where our products go to the other side of the world, they're going to go through some warm temperatures on a ship before they reach their destination, and that will influence the shelf life of products. And we've seen that in real life, where we've had issues, generally microbiologically related issues, as a result of that. So the other thing to think about is that in these days where we're really concerned about the environment and we're concerned about food waste, is that optimizing the shelf life and understanding the shelf life of a product really helps us avoid food waste. So once we can establish some really good shelf life parameters, that certainly helps us in terms of preventing a lot of food being discarded because it has deteriorated. Okay, so I'm very happy to take any questions. And I'll just have a look in the chat box and see what I've got.
We have got a few there. Look, it's Jenny here again. Just keep in mind that there's very much a limit to what Steve can cover in 1 hour, but people have got questions there on some other products as well, Steve, so see how you go. Okay, no problem. So I'll try and start from the top. What is your advice for high protein powders, for example, lactoferrin, WPI, WPC, etc.? Yeah, we do need a lot more data on those. I think with WPC in particular, I have some experience with that. And there are a number of issues with WPC and deterioration due to enzymatic activity, largely because with whey, we are facing a situation where microorganisms have been used in the manufacture of cheese, or microbial contamination has occurred somewhere along the manufacturing chain. So we're not just dealing with the raw milk, we're dealing with a raw product that's come out of a processed environment. And so the shelf life of WPC based on enzymatic deterioration can be pretty rapid depending on the quality of the whey that you receive in the plant. Lactoferrin I don't know much about in terms of shelf life, sorry, and WPI I presume is very similar to WPC. Lactoferrin of course has antimicrobial properties which may give us an advantage in terms of shelf life, but that's quite limited. Next question is, in accelerating shelf life of chilled dairy with temperature, does this potentially select for the wrong organisms and reduce validity? That is a very good question. Yes, that can be the case, particularly if you're looking at
if you're really focusing on microbial growth as your indicator. With enzymes less so, because the enzymes will already be present in the product. So if you're just looking at enzymatic deterioration, I don't think that's going to be a problem. But yes, if there's a variety of different microbial contaminants in the product, yes, that will influence. But I think the way around that is that in most cases, the microorganism of concern dominates. So in many cases, we're dealing with an organism that we know is the dominant organism in that product, and we can therefore base our shelf life in terms of an accelerated shelf life storage on that. So yeah, that's probably my answer to that, is that, yeah, we normally know what types of organisms are involved and be able to make a judgment call based on that. But yeah, it has a limitation potentially in terms of how good our accelerated shelf life storage trials can be. So very good question. Next question is, why is it that date marking of pasteurized milk in Australia is generally listed as used by, but in New Zealand it's best before? Which is more correct? In my opinion, best before is more correct, because the product has been pasteurized and there really are no food safety issues with that. It's pasteurized and chilled. So a best before date is what we definitely prefer in this particular case. Why in Australia they have a use by date is a little bit of a mystery to me, because I thought Australia and New Zealand followed very similar guidelines. So yeah, that's my answer to that one. And I can't really see any reason for having use by date. Probably an exception would be if the milk wasn't stored under refrigeration in a very, very hot environment. There may be potential for the growth of a spore-forming food safety issue, but it really would be a very, very rare situation. Next question is, any specific literature available for shelf life of milk powders? Good question. I don't know offhand, but I imagine there is. I'm certainly aware of enzymatic deterioration of milk powders. And yeah, I'd have to look for something on that. But certainly deterioration of milk powders is a concern, and I'd be very surprised if there is no literature out there on that. So yeah, I mean, if you contact me later, I can certainly do a bit of a search myself if you don't have access to good literature searching, and see if I can find something. But yeah, good question, and yeah, certainly something we can look for. Okay, please provide anonymous. Oh yeah, it's from Jenny. Okay. Next question, the water activity profile that you showed, does it change with different composition and different dairy products? Yes, it does. If I think I get your question correctly, clearly all our products do have different water activities based on the composition. And in some cases that can change over time, for example, with the absorption of moisture and so on and so forth. So the answer to the question is yes. And that's something to watch out for. We need to be aware of water activity. It's one of our key criteria for measuring stability of product, particularly in terms of microbial growth, but also to a certain extent in terms of enzyme activity. Although, as I said earlier, enzymes can actually operate under remarkably dry conditions. How well understood or variable are domestic cold chains? Very good question for dairy products. And how much does this influence or reduce the shelf life versus best case scenario? Yeah, that's something we don't have control over. Domestic refrigerators can vary quite a lot, from about 4 degrees to 15 degrees Celsius. And this sort of thing's been very well documented. And we really are limited in terms of what a consumer will do with their product, and leaving a product on the bench for a period of time. I mean, these sort of scenarios are well documented where people have done that. We have no control over that. And really, it's, I guess, an educational thing with consumers, and maybe we should make it more clear on our products that these should be stored at less than 7 degrees Celsius. But, even with that, I think, sadly, the consumers really don't monitor this very well at all. I know I had to do an interesting survey of the refrigerators in one of the radio station networks in New Zealand and in their office, and some of the refrigerators are so full of food, and that alone was causing problems in terms of the temperature within the refrigerator. So it's a big problem. No real answers to that question other than something we need to be aware of and something that consumers should be aware of too. Okay.
So Steve, I think that's all the questions.
I think so, yeah.
Okay. Yeah.
So I know it's been a bit of a quick run through, but hopefully it's given you some insight in terms of what can be done, and will help you in terms of finding more information that's relevant to your products and your situation.
Steve, I'd like to thank you very much for the work you've put in today's presentation. If anybody has questions, they can either email Steve direct or email me, and I'm happy to put you in touch with Steve, and that would be that's fine. So over the next week or so, if you've got any questions, please forward them. Just a reminder that next week's webinar is with presenter Michael Grima, and his topic is emerging retail trends and packaging technologies. So if you need more information about that, you can also contact me. Lots of thank yous coming through there, Steve. And I also did put a link in for you to provide further webinar feedback. So thank you very much.